Thank you for the introduction. I'm Hiroyuki Ishida. I'm postdoc at the NCTS here. First, I have submitted my title. I decided to talk about the biosciences, but after I checked the schedule, the former two speakers has a word of black hole, so I slightly changed my title with the more darker background of the slide. I like to talk about dark matter production issues in the new MSM. Actually, the model is same as the previous title. Anyway, the background is just I like to talk about the dark matter production issues in the new MSM. This work is done by collaboration with Takehiko Asaka in the Niigata University, and Shintaro Ejima is now postdoc at Leiden University in the Netherlands, and both Kiminogawa and Tomoyoshi, they were the student at the Niigata University. And this talk is based on these papers. Okay, let me start from the introduction. When we see the particle content of the standard model, I just divided into the hierarchies. And when we see this kind of particle content as a puzzle, you can see some missing puzzle here. So this is just my opinion. This is just my private opinion, but adding right-hand neutrino looks quite natural extension of the standard model. And after adding right-hand neutrino, one of the most benefit is neutrino masses. Actually, when we add the right-hand neutrinos into the standard model, we can have the Yukawa coupling of the neutrinos and also the Majorana mass term for the right-hand neutrinos. So we can have two kinds of masses called Dirac masses, which is defined by Yukawa coupling times the Higgs depth, and Majorana mass. And when we write down the mass matrix like this form, and after diagonalizing, if the Dirac mass is much heavier, Dirac mass is much lighter than the Majorana masses, we can explain the tiny neutrino masses. So here we have to ask to ourselves, like this question: how heavy right-hand neutrino is needed? As I explained, the seesaw mechanism can be applied when this formula is valid. But when we write down the allowed region of the Majorana masses in terms of the Yukawa coupling, the horizontal axis denotes the Majorana mass scale, and the vertical axis shows the magnitude of the Yukawa coupling. So on this red line, we can explain the tiny neutrino masses, which are observed at the neutrino oscillation experiment. So actually, when we think about the order 1 Yukawa coupling, we have to impose the super heavy right-hand neutrinos. On the other hand, the small couplings are still okay. So in that case, we can have the GeV or sub-GeV right-hand neutrinos. So what I want to stress here is super heavy right-hand neutrino is not necessary for the extension of the standard model. And from the next, I'd like to explain the neutrino minimal standard model. This is for the new MSM, which I want to consider here. In this model, we just add the 3 right-hand neutrinos into the standard model. So after adding 3 right-hand neutrinos, we can write down, of course, the right-hand neutrino kinetic term, and neutrino Yukawa coupling, and Majorana mass. And in this model, we have one key assumption. Of course, we want to have the seesaw mechanism, so we need to impose hierarchy between Dirac mass and Majorana mass. And also, we want to have some direct detectability. So we constrain Majorana mass is lower than the electric scale. And in this model, the typical magnitude of Yukawa coupling is when we think about the 1 GeV right-hand neutrinos, the typical Yukawa coupling is 10 to the minus 7. And in this model, there are two kinds of physical state of neutrinos. One is called active neutrinos, which is mostly composed by the left-handed neutrinos. And another one is called heavy neutral electrons, which is mostly containing right-handed neutrinos. So for simplicity, from now on, I like to call this heavy neutral electron just like right-handed neutrinos. And here you can see there is one parameter we denote as capital theta, which is defined as Dirac mass divided by Majorana mass. This is quite important parameter. And thanks to this, this mixing, right-hand neutrino can have the gauge interaction like this way. Okay, here, this schematic figure shows the typical mass scale of right-hand neutrinos in the new MSM. We have two heavier guys around order of GeV. These guys are responsible for the seesaw mechanism to realize the tiny neutrino masses, as well as the baryogenesis mechanism. And another guy, the rest one, denoted by N1, is a candidate of dark matter, which is say around the KeV. And this dark matter guy can be produced through this kind of diagram called Wilson withdrawal mechanism. From a thermal burst, the neutrino pair can be produced. One or both of them can be converted into the dark matter candidate through the mixing. And typical creation temperature is around 100 MeV. As you can see, when we think about the large mixing, of course the production amount can be increased. On the other hand, when we think about the large mixing, of course the photon production rate is increased. So we have to care about X-ray observatory. This figure shows the current constraint on the right-hand neutrino dark matter.
Sorry, your dark matter is stable dark matter or decaying dark matter?
Decaying dark matter. And the vertical axis corresponds to the mixing square. And when we want to have the sufficient amount of dark matter through the Wilson withdrawal mechanism, the mixing angle should be obey on this line. And you can see this colored region is already constrained by the X-ray observation, so you can see there is no hope to realize the correct amount of dark matter only through the Wilson withdrawal mechanism. So we can conclude that simplest production mechanism is impossible. And from this constraint, roughly speaking, we have to think about the square of Yukawa coupling is order of 10 to minus 24 when we think about 1 kV dark matter mass. So we have to require the really tiny Yukawa coupling for dark matter. So because of such a tiny Yukawa coupling, this dark matter cannot give a significant contribution to the active neutrino masses. So we can consider the physics of N1, N2, and N3 separately. So in this talk, I just focus on the physics of dark matter. Okay, let me think about the higher dimensional operator effect for the initial condition of the physics in the DMSM. Actually, so far, in the most of the analysis of the baryon asymmetry of the universe and dark matter, no initial value neutrino is usually assumed. So that's the reason why we try to consider this kind of effect. When we allow the higher dimensional operator like this one, the right-hand neutrino could be produced by usual sum of the Higgs scattering. And produced amount of right neutrinos is estimated like this one. There are some numerical factor times this kind of factor. And we assume that our cutoff as a Planck scale. So there is a reheating temperature, there is a factor denoted by reheating temperature divided by Planck mass with some coupling. And of course, when we think about I and J, 2 or 3, we can create the heavier guys. And when we think about I and J equal to 1, the dark matter can be produced through this kind of interaction. And there was a work in previous by these guys, but in this work they conclude that such kind of higher dimensional effect cannot give a significant effect on the baryogenesis and also dark matter. But the reason is as follows. As I mentioned, produced amount of right neutrinos is estimated by this form. And in their analysis, they consider the reheating can be governed by the Higgs boson decay. So in that case, the reheating temperature is order of 10 to 13 G. Then this suppression factor is 10 to minus 5. So they conclude that such an effect is not so significant. But here we just line ourselves to the reheating temperature. Okay, let me explain about the effect on the dark matter production. Here we just assume that the mixing between the dark matter and active neutrinos are really tiny. So in this case, the widow mechanism does not work at all. So in this case, the production by a higher dimensional operators becomes most important. This is the result. The horizontal axis is the dark matter mass, and the vertical axis is the required amount of the initial condition. Upper right corner of this red line is forbidden from the overabundance of the dark matter. And when we think about how much? 10 keV dark matter, the required amount of initial condition is of 0 to 10 to minus 3. And when we think about 10 to minus 13 GeV for the reheating temperature and order 1 coupling, the required amount of the dark matter mass is around 5 GeV. However, in this case, as I mentioned before, the dark matter can easily decay into the photon and neutrino. So, by some reason, we have to forbid this kind of mixing. So we need to, in this case, we need to suppose the Zitsu symmetry. But under this Zitsu symmetry, of course, this higher dimensional operator is invariant, so we can produce sufficient amount of that. Okay. But on the other hand, because we forbid this kind of decay, the test for this kind of dark matter might be difficult.
If you impose a Z2 symmetry, then your dark matter becomes stable.
Yes. In that case, in this case, our dark matter is completely stable dark matter. And in other words, we can predict the heating temperature. Here we just assume the coupling of a higher dimensional operator is just universal. I mean, Aij is equal to 1. I just put the reheating temperature in terms of the cutoff scale. And this red line shows the effect on the baryogenesis. And above this red line, we can have the more than 10% contribution to the baryon symmetry of the universe. And when we think about 10 kV dark matter, we have to this line corresponds to the production produced amount of dark matter is correspond to the observed amount. So I mean the left upper corner from this line is constrained over 1 ton. And when we think about more heavier dark matter, the line becomes more light level. Apart from the Dodelson withdrawal mechanism, we might have another dark matter production mechanism called the CPR mechanism, where the resonant production can be occurred with a really large amount of lepton symmetry. There was previous work done by this collaboration. When we think about the heavier right-hand neutrinos is 2.5 GeV, and this is one of the parameters in the Yukawa couplings, and this is mass degeneracy between the two heavier right-hand neutrinos. And within this red line, the baryogenesis can be successful, as well as the dark matter production to this resonant production. But as you can see, the unit of vertical axis is electron volt, so we have to assume the really tiny amount of mass degeneracy between two heavier right-hand neutrinos. But when we think about the higher dimensional operator, of course, that parameter stress might be changed. So we have to re-evaluate the dark matter production, including the higher dimensional operator. But this work is our future work. Okay, let me conclude my talk. I've talked about the model called the new MSM, which is I think it is the most economical extension of the standard model by 3 right-hand neutrinos with the masses below the electric scale. And in this model, we can explain dark matter and the neutrino masses via type 1 seesaw and also baryogenesis. And because we constrain our right-hand neutrinos lighter than the electroweak scale, we have a testability for right-hand neutrinos. And as I mentioned, the simplest production mechanism called the Dodelson withdrawal mechanism is conflict with the observation. So here I have presented the impact of higher dimensional operator on dark matter. The higher dimensional operator could help to produce dark matter abundance, and also the variance symmetry could also be improved. And because of time, I was not able to mention about the baryogenesis mechanism, but the effect on baryogenesis mechanism is also very interesting. On the other hand, when we think about the reheating temperature is much lower than the cutoff scale, such a higher dimensional operator effect becomes negligible. Okay, that's it. Thank you very much.
Any question, comment? Please.
So you mentioned in the later production mechanism of your dark matter neutrinos, you need the resonant production, and it requires some lepton asymmetry.
Yeah, when we want to consider about without the higher dimensional operator, we have to require a huge amount of lepton symmetry for the resonant production.
Another question? One question is because you are based on the new MSM framework, right?
Yes.
And you already set some scale there. And but here you have to introduce another lambda scale to consider the higher order term.
Yes.
I don't understand why you because you are based on some kind of realizable model.
Yes.
But why you introduce a card there? Because in your model already have a scale there, right?
Yeah, originally, we want to have any scale between the electric scale and blank scale. So, but in that model, as I mentioned, we have some tension between the observation and our prediction. Or we need to require this kind of tuning. I don't want to say this is a tuning, but we have to require this kind of parameter choice to realize everything. On the other hand, when we think about some new physics around the Planck scale, we might have some new ingredient into our model. So we just perform that kind of possibility.
So you mean even the new mechanism could be applied to the Planck scale? You mean?
Yeah.
Other question? Okay, if no more question, let's go again.
Thank you.
And it's time for coffee break.